With Systems Toolkit, we simulate a team of drones patrolling above Washington, D.C. Their flight paths are optimized for maximum coverage and to minimize the risk of collision or interference with other aircraft in the area. The drone flight paths also consider any existing no-fly regions and ensure that the team of drones does not enter restricted airspace. Each drone is equipped with sensors and cameras to capture images and data about the area below. They will then transmit this data to a series of ground sensors in the area. Communication sensors create beams between aircraft, enabling information sharing. These beams are essentially lines between the aircraft, and the beams occur through the connection established by sensors. If both aircraft are in the area viewed by the sensor, they are connected and can share information. As the first aircraft continues to move, the beam connecting the two aircraft will change in length and orientation. The beam is not occluded if another aircraft passes between two connected aircraft, but it might connect to both of the aircraft if they're all within sight of the sensor at once. We describe this information sharing with an example featuring 5 drones and 5 ground-based sensors. The figure on the left, which we will call the connection graph, shows a team of 5 drones that share information. In the current environment, Aircraft 1 shown in yellow and Aircraft 3 shown in green are connected through the sensor at place 2 shown by the yellow lines. Additionally, Aircraft 3 and Aircraft 4 shown in white are connected through the sensor at place 3 shown by the blue lines. As drones move, their connection graphs update, and they collect and share more information about the world. Information sharing is essential for ensuring that a team of drones can detect any compromised agents. Agents make guesses about the status of other drones, which are based on the sensor location measurements. Sharing information within the team is critical to self-policing, allowing to detect which objects are compromised or flying through the no-fly zones. Each agent maintains a belief about the status of the other agents. An agent can either be compromised and cut through the no-fly zone or not compromised and follow the nominal path. The analysis of these no-fly zones helps to update the team's belief, determining whether an object is compromised or not. The right graph shows the probability distribution function of the noise model affecting the sensor data, with an offset from its trajectory. The red line represents the noise model of a compromised agent's trajectory intersecting the no-fly zone, while the blue line represents the noise model of the nominal path. These experiments involve a bimodal distribution, making analysis complicated. Detecting the status of a specific drone solely from one data point is challenging. In the presented scenarios, we have one compromised agent in a team of 5. The compromised agent will always be Agent 5 shown in red. The figure on the left describes the true world state. The binary status of whether each vehicle is compromised or not form every possible world state. An agent must analyze the positions of all the available aircraft to infer what world state the system is in. Such a probability inference refers to an agent's belief, that is, the relative likelihood over the types of agents in the team. There are many ways to represent this belief distribution, but for our demonstrations, we will display belief as an agent's confidence relative to the true state. A value of 1 means that the agent has high confidence that the system is in one state, and that state happens to be the true world state. A low value means that the agent thinks that the system is more likely to be in a state different to the true world state. We will demonstrate the powers of our belief-sharing algorithm for 3 use cases. 1. A faulty sensor. 2. Communication denial. And 3. Adversarial hacking. We first examine the situation where one of the drones has a faulty sensor and is sending random information to the others about the world state. Agent 5, shown in red, is faulty, and the other agents must filter out their false information while also detecting that it is flying through the no-fly region. We display the belief of Aircraft 1 in yellow. As it moves, it collects some data from the other vehicles, gaining confidence in its assessments of their status. At one point, sensor noise causes a brief misclassification, which is rectified in 5 time steps, after the UAV connects with other vehicles. Finally, it converges on the correct world state after it manages to collect an additional observation on the status of Aircraft 5 as well as data from its team members. In the second scenario, an adversary can periodically block connections between the drones and the ground sensors, thereby removing them from the information sharing graph. In this experiment, we block the connections of agents 1, 2, and 4 at 50% of the time. You will notice that there are less connections between agents when compared to scenario 1. Despite this, the team can still converge to the true hypothesis as the information collection is asynchronous. We do not need multiple agents to be connected at once to share information between them. In the final scenario, we should the situation where an adversary hacks into a drone and uses it to attempt to influence the other agents into a false belief. By amplifying the incorrect information, it attempts to fool the team into converging to the wrong world state. Initially, Aircraft 5 recognizes that Aircraft 3 has made a misclassification about its status. By providing confirmation on this misclassification, it attempts to trick the agent into keeping its incorrect diagnosis. Notice on the left graph that Aircraft 3, which connected earliest and most frequently with the adversary, is the last of the group to converge, but it eventually does converge after sufficient information is provided to outvote the influence of Aircraft 5.